Hi everybody, my name is Yannick and I'm going to present our work on HyDiff, our hybrid approach for differential software analysis. This is a joint work together with Corinna Passerano, Marcel Böhme, Yuqing Sun, Huang Lam Nguyen, and Lars Grunske. In our work, we distinguish between two flavors of differential analysis. In the first type, we take into account two subsequent program versions and search for differences in the execution behavior. This is also called regression analysis and is one of the most common differential analysis types in software testing. In the other type, we're only considering one program, but we search for different execution characteristics inside it. This is useful, for example, for site analysis, where we try to find secret-dependent paths. This could be done, for example, by taking two different secrets. With them, we execute the program, and then we check if there's any difference in the execution behavior with regard to a specific side channel. Another example would be the robustness analysis of neural networks. We search for inputs that differ only very slightly, but produce a different output in the network. In this figure here, you can see an overview of our approach. As you can see, we combine fuzzing with symbolic execution. Fuzzing on the one hand side is good in finding shallow bugs. It's a very efficient input generation techniques. But since it uses random mutations, it's very hard to hit very specific constraints in the program, and therefore it's very bad in finding deep broken paths. On the other hand side, symbolic execution, it performs a systematic exploration, and it's known for its input reasoning abilities. However, it's also known that it suffers from path explosion and complex constraint solving. While the combination of fuzzing and symbolic execution in a sequential manner is already known, we combine it in a parallel manner, which means that we execute fuzzing and symbolic execution at the same time, and from time to time they exchange interesting inputs. This helps to further amplify the overall exploration. Please also note that we perform a differential analysis, and this is a hard problem because we in general have to reason about multiple paths at the same time. In the next few slides, I will give you an overview about the different stages of HyDiff. So let's start with the inputs. HyDiff requires at least one seed input to drive the initial exploration. But if you have an existing test suite, of course, you can incorporate it. We also need the program under test. And here we distinguish between fuzzing and symbolic execution. For fuzzing, we take the actual program and instrument it, for example, to measure the program coverage. And for example, for regression testing, of course, we need several program versions. For symbolic execution, we take a change annotated program. And here we distinguish between two different change types. These changes can happen inside the program code, which would then be used for regression testing. Here we adapt and extend the change annotations by Palikareva et al. And they use these change annotations to unify two program versions in order to be able to efficiently symbolically execute it. For example, if you have an updated assignment, you can add this change function call, where the first parameter would represent the old expression and the second parameter the new expression. A second type of changes would happen in the input. This enables site analysis and robustness analysis. Here we use a similar notion as for change annotation. So we also have here this change function call, but here we do not have old and new version, but we have two different inputs which get unified to one input. For our fuzzing component, we apply a gray box fuzzing approach. So we build upon AFL, which is a genetic algorithm. So essentially it's a mutational fuzzing approach. And the most interesting part here is the actual mutant selection, which determines which inputs are kept for further mutations. In order to drive this, we apply differential heuristics. So we keep inputs which show output difference or decision history difference. With decision history, we mean the branching behavior inside the program. For the side analysis, we also incorporate the cost difference. And for regression testing, we incorporate the patch distance. The patch distance is interesting when you want to direct fuzzing into the changed areas. Additionally, we also apply here the branch coverage. For our symbolic execution component, we build upon a dynamic symbolic execution inside Symbolic Pathfinder. The central data structure here is a trie, which is a compact representation of a symbolic execution tree. While I talked about the mutant selection in fuzzing, here in symbolic execution, I will talk about the node selection. So in the symbolic execution tree, we would like to select the most promising node for further exploration. This is done by, again, differential heuristics. If you remember, in the symbolic execution, we have these change annotations in the program, and we specifically drive the decision history difference. So this is the most important metric for our differential symbolic execution, but as well, we have also the cost difference and the patch distance. And again, this process is also guided by branch coverage. The output of HyDiff is then eventually a set of generated inputs, which are classified by the divergence. So for example, output difference or convo flow difference. In the evaluation, we perform several experiments in the already mentioned application scenarios, for example, regression analysis, such analysis, and robustness analysis of neural networks. The goal here was to compare HyDiff with its component in isolation. And on this slide, I will give you a brief overview of the obtained results. For regression analysis, HyDiff was able to classify all subjects correctly, which means if there is a subject which actually has an output difference, then HyDiff was able to find it. In contrast, fuzzing and symbolic execution were not able to identify all of them correctly. Additionally, HyDiff was able to generate significantly more output and decision differences. For our sidechain analysis, HyDiff showed some very good trade-off between symbolic execution and fuzzing. However, it was not able to show a significant amplification of the acceleration in contrast to regression analysis. The reason here is that differential fuzzing is already a very powerful tool for this problem domain. Therefore, the combination with symbolic execution did not show so much benefit besides the combination of the results. Finally, the robustness analysis of neural networks was a really stress testing application for HyDiff. This analysis is very expensive and complex. But still, HyDiff was able to generate significantly more output differences than the components in isolation. All right, so this was a very brief introduction to HyDiff. If you want to get more details, please check out our paper and also our artifacts. They have been evaluated and they are available online on GitHub. Thank you for your attention, and I'm happy to answer any questions.